Hello learners, welcome to NIOS. I am Ekta Mathur. Previously we have discussed about the chapter 23 and today I am going to tell you we will learn about the lesson 25 of chemistry, compounds of carbon containing halogens, haloalkanes and haloarenes. At the end of this lesson you will be able to define haloalkanes and haloarenes. You will be able to name haloalkanes and haloarenes according to IUPAC rules. You will be able to explain methods of preparation, physical properties, chemical properties and uses of haloalkanes and haloarenes. You will be able to explain the preparation, properties and uses of some important polyhalogen compounds. Now let us begin with what are haloalkanes and haloarenes. When a hydrogen attached to a carbon atom in a hydrocarbon is replaced by halogen atoms like fluorine, chlorine, bromine or iodine, the compounds so formed are called haloalkanes or haloarenes. The halogen derivatives do not occur in nature and they are synthesized in laboratory. Previously, in the previous chapter, I have told you how to name an organic compound. There are certain rules. So, the same rules are followed while naming haloalkanes and haloarenes. The first is the longest chain of carbon atoms need to be selected, which bear the halogen atom. Numbering of carbon atoms in the chain is done in such a way that carbon atom bearing the halogen atom get the lowest number. The word chloro is prefixed to the parent hydrocarbon name. In case of alkyl substituted haloalkanes, the longest chain containing halogen atom is selected for numbering. When two or more halogen atoms are present in a compound, the longest chain selected must contain the maximum number of halogen atoms. The multiplicative prefixes like di, tri, tetra are added before the name of halogen atom to indicate the number of halogen atoms. Let us look at a table and see that what could be the name when the halogen is attached. If see the first example CH3CH2Br, so it will be called as bromoethane. So, we have prefixed halogen before and then the name of the hydrocarbon. Let us see the fourth example CH3CH, CH3, CH2Cl. So, we will number it from where the halogen is. So, 1 chloro, then you have 2 methyl and the chain is of propane. So, likewise we name the halogen compounds. Aromatic hydrocarbons containing halogen, that is haloarenes, you have a chlorine as a side chain in benzene. So, it will become chlorobenzene. So, here also we are using prefix chloro and then the aromatic compound name, that is benzene. And further you have a substituted CH3 also. So, it becomes the 2-chlorotoluene. Because why it is so? Because toluene is preferred as number 1. So, 1 and 2. So, at 2 position you will find chloro. So, 2-chlorotoluene and so on, which we have already discussed in lesson 23. Let us learn about the preparation of haloalkanes and haloarenes. So, as you can see from here, we can prepare haloalkanes from hydrocarbon. So, here I have taken hydrocarbon ethane reacting with chlorine in presence of sunlight at high temperature in dark. The conditions are more important to form a required or designated product. So, here if you take bromine, you form bromoethane. With iodine, there is no reaction as the reaction is reversible, and fluorine do not react at all because it is highly reactive. We can also prepare haloalkanes from alcohols. So, let us take one reaction with hydrogen halides. When you react ethanol with HCl in presence of anhydrous ZnCl2, the product form will be chloroethane and water. What is the role of ZnCl2 here? It absorbs water and prevents reverse reaction. Another one you see that when ethanol is reacting with HBr in presence of concentrated H2SO4, which is refluxed and heated, you get the product bromoethane and water. You can also prepare haloalkanes from reaction with phosphorus halides. When I am talking of phosphorus halides, it is PCl3 as well as PCl5. Here the important thing to note down that one product will be haloalkanes, like if I take an example of ethanol reacting with PCl3 phosphorus trichloride, you get chloroethane, but the one product here is phosphorus acid H3PO3. And if you react alcohol with PCl5, you get chloroethane, but the another product vary here, which is POCl3, phosphorus oxychloride. So if you write the reverse reaction, it will be wrong. You need to remember that with PCl3, the one product is phosphorus acid, and when you are reacting with PCl5, it is phosphorus oxychloride. You can also prepare haloalkanes by taking alcohol and thionyl chloride. The formula of thionyl chloride is SOCl2. You get chloroethane, SO2 and HCl. Both SO2 and HCl are escapable gases, so this is the best method for the preparation of haloalkanes. Preparation of haloarenes. Now when I am talking of arenes, yes, of course, benzene will be there. So you take benzene and you are reacting with halogens, say chlorine, bromine. When you react with, in presence of Fe and FeCl3, you get a haloarene or a halobenzene. If you are taking chlorine or bromine, it will be halo, that means bromobenzene or chlorobenzene, whatever halogen you have taken, plus HX, any halo acids. When you react with iodine in presence of HNO3 and HiO3, you get iodobenzene plus Hi. The Hi so obtained will react with HiO3 to form iodine and the reaction continues. You can also prepare haloarenes from diazonium salts. So first of all, let us form a diazonium salt. Benzene having an NH2 group is called as aniline, which is reacted in presence of NaNO2, sodium nitrite with dilute HCl, and the temperature is maintained as 273 to 278 Kelvin or 0 degrees Celsius. You form the product called as benzene diazonium chloride. You see the structure, how it is made, which is most important. Then benzene diazonium chloride is further reacted by, if you are reacting with CuCl and HCl, you will get chlorobenzene and nitrogen. If you are reacting with CuBr, copper bromide and HBr, you will get bromobenzene. So it depends upon you are reacting with what reactants. If you warm it with Ki, potassium iodide, you get iodobenzene. But fluorobenzene can also be prepared from NaNO2 and HbF4 in a range of temperatures 272 to 278 Kelvin. You get fluorobenzene plus N2 plus BF3. Next, you can also prepare chlorobenzene or bromobenzene by Getterman reaction, in which you are using metals like copper metal. So you take benzene diazonium chloride and react with copper metal plus HCl, you get chlorobenzene and nitrogen, and when you react with copper metal and HBr, bromic acid, hydrobromic acid, you get bromobenzene, nitrogen and Cl minus. So this is all we have learned, how we are preparing haloalkanes and haloarenes. These are various reactions, you get the desired product. Now let us study about the properties of haloalkanes and haloarenes. When I am talking of properties, yes, of course, physical and chemical properties. But before that, we should know what is the nature of CX bond. In alkyl halides, the carbon halogen bond is formed by the overlap of sp3 hybrid orbital of carbon atom with the p orbital of halogen atom. As one moves from fluorine to iodine, the size of the halogen atom increases. Hence, the overlap decreases. Hence, the CX bond becomes longer and weaker on going down from alkyl fluorides to alkyl iodides. Also, we know that halogen atom is more electronegative. The electron density along the CX bond is displaced in the direction of halogen. Thus, CX bond is polar in nature. The carbon atom bears a partial positive charge and the halogen atom bears a partial negative charge. The partial positive charge carbon in haloalkanes can be easily attached by anions. An electron-rich species, which we call it as a nucleophile, can attack carbon. On the other hand, the partial negatively charged halogen atom can be attacked by the cations and electron-deficient species. Physical properties. When we are talking of physical properties, yes, of course, we are talking about whether they are liquids or gases, and boiling point and melting point. So, the lower alkyl halides like CH3F, CH3Cl are gases at room temperature, and the other alkyl halides containing up to C18 are liquids having high boiling points, and the higher members are solids. Haloalkanes and haloarenes are moderately polar molecules. Still, they are immiscible in water. It is due to their inability to form hydrogen bonds with water molecules. The melting point and boiling point when we are talking of haloalkanes and haloarenes are higher than those of the parent hydrocarbon. This is because greater the molecular mass, the greater the magnitude of van der Waals forces of attraction, and so the greater will be the melting point or boiling point as compared to the parent hydrocarbon. All monohalobenzenes are liquids at room temperature. Among dihalobenzenes, the para-isomers have the highest melting points. It is due to the greater symmetry that causes a better packing of molecule in the para-isomer. You can observe the table in which the comparison of boiling points is given. Now, let us study about the chemical reactions, chemical properties. So, halo compounds undergo 4 types of reaction. One is substitution, another is elimination, reaction with metals, and reduction. So, first of all, let us see how the substitution reaction takes place and what are the nucleophiles, which I have already explained you in lesson 23. So, when a haloalkanes is reacting with a nucleophile, so it will form, if suppose you are taking a nucleophile as alcohol, it will be forming C2H5OH plus Cl minus will be eliminated. So, there are 2 types of nucleophilic substitution reactions, SN1 and SN2. So, here when you are substituting X with an OH or any nucleophile, it will form an alcohol. If you are taking NH3, it will be forming alkylamines. If you are taking CN, it will be forming alkyl nitriles. If you are taking SH, it will be forming thiols. If you are taking an RNH2, it will be secondary amines. If you are taking OR, alkoxy group, it will be forming ether, and so on. So, let us learn about the nucleophilic substitution reactions. Nucleophilic substitution reactions are of 2 types, SN1 and SN2. Why SN1? Because nucleophilic substitution unimolecular, and SN2 nucleophilic substitution bimolecular. So, let us see about the mechanism first of nucleophilic substitution bimolecular SN2 reaction. Now, as you are observing here in the figure, OH is a nucleophile which is attacking to an alkyl halide. This alkyl halide is a primary alkyl halide because on all 3 sides you have hydrogen and one it is chlorine. You observe that OH attack from the back side and slowly chlorine will go. So, this is state which we call it as a transition state. Here the carbon is more. So, it is not now tetravalent. So, what is happening in this state? OH is going and attacking carbon and chlorine will leave the carbon. So, this is called as an attacking group and chlorine is called as a leaving group. So, it will form finally alcohol. So, please note down that most importantly, it is a one-step reaction. It is a single step process. OH here is acting as an attacking reagent or an attacking group and chlorine act as a leaving group. It involves a transition state as you have seen in the figure. It proceeds with inversion of configuration. You find that these atoms are getting inverted as an inverted umbrella. Fifth, the rate of reaction depends on 2 reactants. Which are those 2 reactants? Nucleophile OH and the alkyl halide. So, that is why it is called as nucleophilic substitution bimolecular. The order of reactivity is 1 degree, more reactive, then 2 degree, then 3 degree. Why is it so? Because suppose I substitute this H with CH3, then one CH3 group has its effect also. So, it will be having a plus I effect which we have already discussed in lesson 23. If you place more of the alkyl groups, the incoming nucleophile will be having a difficulty to attack the carbon. That is why the ease of reactivity is 1 degree is more reactive, then 2 degree, then 3 degree. So, let us learn about the mechanism of substitution nucleophilic unimolecular SN1. Here I have taken a different halide and that is not now primary, it is a tertiary halide. When you react tertiary halide and when first you need to break the bond. So, when you break the bond, this process is slow process in which it results into the formation of tertiary carbocation and Br minus is liberated. In step 2, the nucleophile OH ion will come and attack. Now here it is not attacking from the back side or front side. It can attack any side. So the tertiary carbocation will attack OH, and when this reaction takes place, it is a fast reaction. So from here you cannot find the rate of reaction. So the rate of reaction will be depending on only one reactant. That's why we call it as a SN1 or unimolecular nucleophilic substitution reaction. So here you find that alcohol is formed. So please note, it takes place in 2 steps, one this and one. Second one, first step is slow and rate determining step, so we call it as a substitution nucleophilic unimolecular. Fourthly, second step is fast and it does not involve transition or inversion of configuration as we have seen in SN2 reaction, and the order of reactivity is reversed. There in SN2 it was primary, secondary, tertiary, but here it is tertiary, secondary and primary. There is a logic behind it. Why it happens? Because tertiary carbocations are most stable, due to which effect we have already discussed, due to plus I effect or hyperconjugation, which all these effects I have told you in lesson 23. Next reaction is elimination reaction. When haloalkanes are heated with aqueous solution of potassium or sodium hydroxide, the major product formed is alcohol, as you can see from the equations. C2H5Cl aqueous KOH gives you alcohol. But if you take alcoholic KOH, then the products are different. That is, here the OH is acting as a base. So it removes a proton from the molecule and the product form will be ethene. So there was a difference. Aqueous KOH gives you alcohol when react with C2H5Cl, or when you react with alcoholic KOH and alkyl halides, you get an ethene. If the structure of alkyl halide is such that it can undergo elimination in 2 different ways, then which alkyl halide will be preferred? That is decided by Sidzeff rule. What does the Sidzeff rule says? That if more of the substituted alkenes are there, then that alkene will be preferred which has more number of alkyl groups on either side of the double bond. For example, we will take 2-bromobutane. Let us see this example, CH3CH2CHBr, 2-bromobutane, when it reacts with alcoholic KOH. So I am taking alcoholic KOH, so there will be double bonded compound formed. There will be 2 double bonded compound formed, but2-ene and but1-ene. But but2-ene is 80% obtained and but1-ene is 20% obtained. Next is reaction with metals. When you react haloalkanes and haloarenes with a variety of metals such as zinc, magnesium, lithium, etc., the compounds so obtained are called as organometallic compounds, and we also call it as Grignard reagent. So when chloroethane is reacting with magnesium in presence of dry ether, you get ethyl magnesium bromide. You can see more examples like 2 molecules of alkyl halide on reaction with sodium metal will give you a hydrocarbon. If you react bromoethane with lead in presence of dry ether, you get tetraethyl lead, which is used as an anti-knocking agent in gasoline for running automobiles. Wurtz reaction is another example in which we are reacting haloalkanes or haloarenes in presence of sodium metals. So one is Wurtz-Fittig reaction. In Wurtz-Fittig reaction, what you need to pay attention is here, you have taken 1 molecule of chlorobenzene reacting with 2 atoms of sodium, and another molecule is chloro or haloalkanes, CH3Cl. So one is C6H5Cl and other is CH3Cl. It will form toluene and sodium chloride. Fittig reaction. In Fittig reaction, you are taking 2 molecules of chlorobenzene and reacting with metal in presence of dry ether to form diphenyl. Last reaction is reduction. So haloalkanes can be reduced to the corresponding alkanes. For example, when you take bromoethane and react with hydrogen in presence of nickel, platinum, palladium, you get ethane or HBr. Some useful polyhalogen compounds like chloroform. Chloroform is a derivative of simplest hydrocarbon, methane, and its IUPAC name is trichloromethane. You can obtain it from ethanol. So, here is the chart how you can obtain it from ethanol. Ethanol will react with chlorine to form ethanol, and then from ethanol you form trichloroethanol, which further gives you chloroform. The products so form trichloroethanol, when you react with calcium hydroxide, you get chloroform. So, there are various methods to obtain chloroform. You can also get it from propanol or acetone. You get the product, that is trichloroethane, and then you react with calcium hydroxide, form calcium acetate, and you get chloroform. So, you can obtain it from alcohol also, you can obtain it from propanol also. Chloroform is a colorless, sweet smelling liquid with a boiling point 334 Kelvin. It is slowly oxidized by air in presence of light to a poisonous gas called as phosgene, whose formula is COCl2. Therefore, chloroform is stored in dark colored bottles to prevent it from sunlight. The bottles are completely filled so that the air is kept out. Even a small amount of ethanol, if added to a chloroform, will convert to toxic phosgene if formed into a non-toxic compound, ethyl carbonate. So, you can see the equations below. Next, chloroform is also used in isocyanide test for the amines, for the detection of primary amines using alcoholic NaOH, which you are going to further study in the chapter amines. Next is iodoform, which is also called as triiodomethane, a pale yellow solid which can be prepared by heating it with iodine and NaOH. You get CHI3. So, in further chapters to come, you will understand the preparation of iodoform. Next compound is dichloro-diphenyl trichloroethane, which is also called as DDT, and it is actually found in different forms in products of in powdered form, in aerosol or granules. It is used mainly to control mosquito-borne malaria diseases. It is also used as agriculture medicines. It is used as in insecticides, and nowadays the use of DDT has been banned because it is not biodegradable, so it harms the organisms such as fishes, birds, etc. So, this is all we have learned about the haloalkanes and haloarenes, the important compounds and the derivatives, the various reactions which are taken forward by the haloalkanes and haloarenes. Thank you. Hope to meet you again.